Chapter 1, Introduction to the Scientific Method. This is a great way to begin our study this semester. This chapter really gets into some good information about how science works and how we find out about the world around us. And really, it's going to be the foundation for the rest of the semester because everything we learn from this point forward has been determined through experiments through the scientific method. So this really gives you some insight into how scientists think. The scientific method is a process, and it's a process that is helping us solve problems and answer questions about the world around us. It is a very logical, systematic, thorough method of investigation. Scientists are real big on working through things logically, making sure we don't leave anything out, not taking anything at face value. I mean, everything has to be proven, and that's what the scientific method is all about. Truth in science is a very important concept for you to understand because it's not like truth in the other fields. So it's not ultimate truth. So truth in science is defined as what we know and understand based on all currently available information. So that leaves open the possibility that truth could change. So a true scientist is always open to that more data, more information could mean that what they believe to be true may end up being proven false in the future. Understanding the scientific method will help you as you judge and evaluate information that you see or hear in the news, in magazines, and probably most importantly the internet for its accuracy and its dependability. As many of y'all probably know, especially if you looked under the faculty information page on Blackboard, I'm actually a small animal veterinarian. And so one common thing that I'll hear clients say when they come in to see me and their pet is sick or whatever is they'll say, well, I know I'm not supposed to do this, but I looked on the internet and this is what I found. And then they'll say, whatever it is they found. And the internet really is not a bad resource. It's actually got a lot of good information. It's just got a lot of bad information too. So you've got to kind of sift through that. You should evaluate the websites you go to, the journal articles, anything you read. You should not take for granted that it's accurate. So while you can definitely use the internet for medical research, either for yourself or for your pet, you do have to be very careful about that. So there's actually an excellent section of this textbook, a chapter, about how to evaluate websites and how to go about determining whether or not a website is likely to be accurate as far as the scientific information portrayed there. The scientific method is composed of 5 steps. The first step is that you make an observation of the world around you. So that's kind of the beginning point to an investigation, is you're kind of wondering something about the world around you. So that kind of leads into step 2, which is you propose an idea about how something in that world works. So that idea, that proposal of the idea is called a hypothesis. A good hypothesis must be testable, so you have to be able to design an experiment around it. Otherwise, it doesn't really help you to prove anything if you can't test it. It also must be falsifiable, and that's kind of a big word that means it must be able to be proven false. And that seems a little bit odd that you're trying to prove something false, but you have to realize that from a scientist's perspective, it's a whole lot easier to prove something wrong than to prove it right. It's actually very, very difficult to prove any hypothesis to be true. In fact, scientists will not even say that. They'll say that the evidence or the data supports a hypothesis, but they are very cautious about saying that a hypothesis is true just because of that whole concept of truth in science that we've talked about a little bit earlier, which is that whenever you find out more information, you may be able to prove something wrong that you originally thought was true. So typically when we talk about a hypothesis, we're talking about proving it wrong rather than proving it right. The third step in the scientific method is you make a prediction about what will happen when you test your idea. That typically takes the form of an if-then statement. So if I do such and such, then such and such will happen. Your prediction should be stated so that it can be clearly rejected if it's not true. Step 4 is you test your idea, and we call that testing an experiment or experiments. A well-designed experiment is going to be tightly controlled So every aspect of the experiment is controlled by the experimenter or by the scientist. And the reason we do that is we're trying to reduce bias. Bias is the influence of a scientist's or research participant's opinion on the experimental results. So, for example, if you were participating in a study where you were taking a medication that was supposed to reduce joint pain, you might end up reporting favorable results of the medication because you believed it worked, even though it may not have actually done anything. So to compensate for this bias, what researchers will do if they're doing like a test on a drug is they'll actually have one group take a placebo or a pretend medication and not tell the participants which group they're in, whether they're in the placebo group or the group that actually took the medication. And so that way it kind of eliminates bias. And so when you look at the reports of the study at the end, there's always going to be a difference or an improvement in the placebo group, even though they didn't even take a medication. And so that is bias, is the opinion of the experimenter or of the research participant, and how that influences the experiment. So when you're testing your idea, when you're designing your experiment, you need to be able to collect data or information. It needs to be measurable. So we always test things that we can measure. We don't ever try to test something that we can't measure, because otherwise you don't have any results. Alright, so step 5 of the scientific method is to analyze your results. And when you do that, you're going to discard or modify your idea in response to those test results. So typically we use statistics to analyze results, and we're going to get into statistics just a little bit in this chapter. Not a whole lot, but just a little bit, so you can kind of understand some basics. But one thing you'll see repeated in experimental reports is the phrase statistically significant. And what that means is that the results are unlikely to be due to random chance alone. So something is statistically significant. It's a big enough difference that we don't think it's just random chance. So you'll see that phrase quite a bit, and that's kind of important to understand. Once you've analyzed your results, you may be able to support a scientific theory or create a scientific theory based off of what you found. So anytime we've done, scientists have done a whole lot of research or a whole lot of experiments in one particular area, and all of the data seems to support one truth, they will often call that a theory. So an example of that would be like cell theory. All the research we've done, as far as how the cell is designed, what the cell does, the components of the cell, we still call that a theory, even though many experiments have shown that it's very likely to be true over time. Another really important concept you're going to come across in this chapter is how to evaluate scientific information. And you can't look at scientific information the same way you would look at other historical information or philosophical information. It's kind of a different way to analyze that. So the first thing you'll come across are the terms primary versus secondary sources. A primary source is the original source. So if a group of experimenters design an experiment and then they report that result in a scientific journal, they are the primary source. A secondary source is kind of one step removed from that. So if a news report reports a study in a scientific journal, the news report would be the secondary source. So obviously a primary source is better than a secondary source just because there's going to be less of a chance for the data to have gotten misconstrued or misunderstood between the primary and the secondary source. Another important concept is the idea of a peer-reviewed experiment or a peer-reviewed journal. What that means is if a scientist designs an experiment and then they record the results and they submit that in a journal, if it's submitted to a peer-reviewed journal, that means other scientists can critique the study and critique the results. So typically you're not going to submit something to a peer-reviewed journal unless you're pretty confident that you did a good job on it. So that's something you can really use to evaluate things you find on the internet is, was this experiment or was this drug ever reported to a peer-reviewed journal so other scientists could comment on it. Another thing that you need to understand is the difference between correlation and causation. So if two things are correlated, then there is a relationship or connection between them, but it does not mean that one thing caused the other thing. So for example, there might be a correlation between cold weather and the flu, but that doesn't mean that the cold weather necessarily caused the flu. You might have gotten the flu because your kids went back to school and they were exposed to it and brought it home. or it could be because people are more stressed in the fall and the winter, and so their immune system is poorer and they're more likely to get the flu. So there are a lot of different factors that could contribute to the idea of a flu season other than just the weather. There's a correlation, but not necessarily a causation. From a scientist's perspective, it's a lot easier to prove a correlation than to prove a causation. To prove a causation, you've got to eliminate every other possible cause. To say that A caused B, you've got to eliminate every other possibility of something that could have caused that instead, and that's just very, very tricky to do. So usually scientists will say there's a correlation between these two factors, rather than to say that one caused the other. Any good scientist is going to do a repeatable experiment. So when they outline how they did it, another scientist should be able to read that and repeat the experiment, and they should get the exact same results. So a repeatable experiment with reliable results is very important. Kind of what goes along with that is that as many conditions are controlled in the experiment as possible. So you're trying to rule out any confounding variables, anything you didn't think about that could have influenced the result. Also, a good scientist will openly acknowledge the limitations of their experiment or their study, and you'll find a lot of peer-reviewed journals at the very end of any of the articles. The experimenters will talk about what could have gone wrong, what might be something they could do in the future to make a better experiment or design a better research experiment. So scientists are very open as authors to acknowledging their limitations. All right, so evaluating scientific information using the scientific method is a type of critical thinking. And when we talk about critical thinking, what we mean is that that's a way of deciding whether something is always true, sometimes true, partly true, or false. So you're not taking anything at face value. You're evaluating whether that entire statement is always true, sometimes true, partly true, or just completely false. And you will apply the critical thinking skills that you learn in this chapter to the rest of the semester. We've already mentioned bias a little bit. Definitely watch for bias because you will see it. There is no way to escape bias. You're going to see it in the textbook, and you're going to see it with me. You're going to see it with the instructor. So one good example of this is that the textbook is biased towards evolution, the theory of evolution. So you're going to see that whenever you're reading in the textbook, and that's okay. Just realize that and kind of accept that and move on. The instructor is going to be biased towards creationism. So one thing I'm going to do this semester is really try to give you kind of both sides of that debate, because that's a decision that you need to make based off of your critical thinking skills as far as which side you're going to tend to align more with, whether you are more predisposed to evolution or maybe more predisposed to creationism. But I'm going to try to make sure that you get exposed to both this semester. So you should always look at the relevant data, and this really goes back to anything, but definitely creation versus evolution, and then make a decision for yourself. A good scientist is not going to try to tell you what you should think. They're going to give you data and let you make that decision yourself. So this chapter really is a great introductory chapter. I was very pleased with Textbook wrote it. I think that you'll find it interesting, and I hope that you can apply it to your life in general and also just to the rest of the semester.